In this video, I'm going to describe how CMOS logic outputs work. Along the way, I'm going to explain the top 5 most common mistakes people make when designing with CMOS logic outputs, in no particular order. The first mistake people make is bus contention. This means having more than one output driving the same line at the same time. The second issue is around understanding the clamp current and output current specifications in the datasheet, or perhaps I should say misunderstanding them. Similarly, output voltage is often misunderstood. It's common to see CMOS devices that are excessively loaded, meaning that they have too much capacitance at the output. And finally, it's common to see transmission lines being driven without proper termination. Just like in my video about CMOS inputs, I'm going to talk about how the outputs work, and along the way, I'll bring these up. If you watched my video on CMOS inputs, this circuit will probably look very familiar, because this is the most common circuit used for CMOS inputs. But it's also the most common circuit used for CMOS outputs. In the case of outputs, the output is over here, and the internal logic is on this side. So in this video, we're going to be concerned with how much current the PFET can drive at the output, and how much the NFET can sink at the output. We're also going to be talking about exactly what the voltage out here is, and different aspects of loading and how that affects the output. One of the things that makes analysis of this type of circuit relatively easy is the fact that the internal logic here is going to either drive VCC or 0 volts on this line. So that means our MOSFETs here will always have a control voltage of VCC when they're turned on and 0 when they're turned off. You can see this from looking at VGS for the NFET, and that will either be VCC or 0. And for the PFET, you're going to have the same VCC or 0, just with the opposite state here. Really, when you're looking at the output of a CMOS device, you're looking at a single MOSFET. In the case where the output is driving low, or the control is VCC, then that means the NFET is going to be turned on, sinking current, and the PFET is completely off. It's in the cutoff region. You can also reverse that and have the NFET off and the PFET on, and then you'll be driving high at the output. But what's important here is to figure out exactly how this output will behave under different conditions. For example, if we connect a capacitive load, and let's say we have a 5-volt system here, if we were operating at 5 volts, then our capacitor would be charged to 5 volts when the output's in the high state. And when we switch to the low state, we assume that this switches very quickly, within nanoseconds. Then our MOSFET down here turns on. This one's off, so it's not contributing anything to our conversation here. And the question is, what does this capacitor do when this MOSFET is turned on instantaneously? So in order to answer that, we're going to have to look at how a MOSFET works in some detail. If we assume that the gate is going to be at a constant voltage, and in this case it's going to be VCC, then VDS is really the only thing that's going to control the current through our MOSFET. And if you've studied MOSFETs, then you'll remember this curve. To the left of this line, the device is in the ohmic region. That means it's acting a lot like a resistor. So as you increase VDS, you will also be increasing ID, and it's fairly linear. To the right of this line, the current is relatively constant. It will be increasing. This won't be a perfectly flat line, but this is acting a lot like a constant current source at this point. Now, the value of VCC will be one threshold above this transition. So this is VCC, and from here to here is going to be the threshold of the device. You don't need to know the threshold of the device in order to use it, But it's good to know if you drive your output, which is right here at the drain, all the way up to close to VCC when the device is in the low state, then you're going to push it into saturation. The trouble usually is that saturation for many logic devices is going to be at a much higher current than what the device can actually handle. So now that we know how this MOSFET works, let's look at how we would expect it to behave whenever it's suddenly switched on and our output capacitor is fully charged. So I'm going to mark this as VCC, and we're going to say that our capacitor is sitting here fully charged, just waiting for something to happen. And then suddenly we're going to switch this on at this point, and we'll see that this starts to immediately discharge the capacitor. But remember, the voltage across this MOSFET right now is VCC, so that means that we're in the saturation region. Our MOSFET is going to be sinking a constant current at this point. And in order to exaggerate this, I'm going to draw this as a straight line, and I'm going to draw that straight line down until approximately one threshold down. Now this is probably a bit exaggerated, but I want to show that this is in the saturation region here. Then as the device transitions into the linear region, you'll see this start to level out and go into more of a curve. That's an RC curve. This is, as I said, very exaggerated, but this is approximately what you'll see anytime you switch a logic device. If for some reason this capacitor had much more voltage than what the control voltage is, then you would see this linear region extend out. For example, if we were to have a device that was operating at, say, 1.8 volts for the voltage here, and it was open drain and we had 5 volts on the output, then we would see, assuming this was 5 volts, and 1.8 volts is way down here, then we're going to see when it switches that we're going to have a linear response all the way down until one threshold below 1.8 volts, instead of way up here close to 5 volts, which was my other assumed VCC. You'll find that when compared to a regular RC circuit, if we just removed this MOSFET and replaced it with the equivalent resistor, then it would act a little differently. We're going to see it basically shoot straight down here and then curve out to the end. Although it's going to be very similar, they're not exactly the same thing. The fact that they're very similar, though, makes it a lot easier on us to be able to estimate operation of a device. One of the most common questions I run into is, how do I determine the output voltage of my CMOS device? So if we come over here and look at a CMOS output, assuming, let's say, 5 volts, and our output is connected directly to our circuit. For example, let's put a pull-up resistor here that is a 4.7 k ohm. And let's call this device perhaps 32 ohms. The question is, what's our voltage out here? Hopefully you can see from this pretty easily that when this PFET is turned off, then this NFET is turned on and you have a voltage divider. Whatever this voltage is up here, you're going to see that divided down with the 4.7 K and the 32 ohm. Now, 32 ohms is much smaller than 4.7 K, so your voltage here is going to be very small. By my calculations, it's around 34 millivolts. And for most cases, you could just call that 0. CMOS devices will drive very close to 0, even with a relatively small pull-up resistor. I'd say the next important thing to know is what happens whenever we start varying this supply value. Because in most data sheets, they're only going to give you values at, for example, 1.65, maybe 3.0 and 4.5 volts. You might get some other values or different places, but if you want to know exactly a value at 5 volts, 3.3 volts, 1.8, which are standard values, you're going to have to make some assumptions, or you're going to have to do some calculations from what's given in the datasheet. So let's look at how the resistance of a MOSFET is affected by the supply voltage, or I should say, the control voltage. I'm just going to call the resistance of the MOSFET R on and the control voltage V in here. So if you directly compare these two, there's going to be a point where your device is totally turned off. That's the threshold. So if you go at this voltage or below it, the resistance is going to be infinite or very, very large. Just drawing a dashed line here, that means our R on will have no real answer to the left of this line. This is all high impedance mode. However, as you move to the right of this line, you will see that the resistance quickly drops down, and it's going to level out to some value, and it will continue to slowly decrease as you increase the V in, but not by very much. The important thing to understand here is that if you're operating at, for example, 3 volts, and you want to know how the resistance is going to change when you increase to 3.3 volts, then you're guaranteed that that resistance will decrease. That means that the voltage across this will also decrease, and the amount of current that you can drive increases. Or in other words, the worst case for a voltage range from, for example, 3 volts to 3.6 volts is going to be at the bottom of the voltage range. This is the reason why semiconductor manufacturers always show this value in the datasheet and they leave the nominal value out. They're trying to show you the worst possible case, and if you use the number for RDS on from this, then you're going to definitely design your system to work correctly. Now that we've looked at basically how this works, let's put two outputs onto the same bus. Now, if these two outputs are driving the same data line, sometimes we'll call this number 1 is turned on driving, and sometimes number 2 is turned on driving. This is a very common setup in communication systems where you might have one board that's going to be sending data at one time and another board that's going to be sending data at another time. However, you never want to have both of them attempting to send data at the same time. So we can imagine this: if this device is trying to drive the line high and its MOSFET has a resistance of 10 ohms, and this device is attempting to drive the line low and its resistance is also 10 ohms, then that means we've essentially connected our supply directly to our ground with 20 ohms. That comes out to 250 milliamps of current, and most likely will immediately damage both of these devices and cause this bus to fail. This is something we call bus contention, and it's something you always want to avoid with logic. There are two exceptions to connecting the outputs of devices together when they're active. The first is whenever the devices are inside of the same semiconductor package. So if I have a device that has 3 buffers, for example, an LVC 3G34, then these 3 buffers can be connected directly in parallel as long as the inputs are also connected directly in parallel. There's 2 main factors here that prevent problems. First, because these devices are in the same package, there's going to be very little difference between the 3 sets of MOSFETs. That means timing is going to be extremely similar. Second, the inputs are directly tied together, which means they have the exact same timing. So because of these 2 things, the outputs can be shorted together, and that won't cause you any problems. All it will do will be to increase your drive strength. Essentially, when you're driving low at the output, you will have 3 resistances pulling to ground at the same time. It's actually incredibly uncommon to need to do this. The only time I've seen it really required is if you're trying to push a device all the way to the very bottom limits of its voltage range, or maybe even a little beyond the bottom limits. So what I was showing earlier with the RDS on plot, if you're looking at how resistance increases as you decrease the voltage supply. So if you have a device that's designed, for example, for a 5-volt supply, but you're running it at 2 volts, then you're going to be operating somewhere at the higher resistance end of these MOSFETs. And what you can do to reduce that is you can put 3 in parallel and you'll end up with 1/3 of the resistance instead of this resistance up here. The other case that makes it okay to put outputs in parallel is when the outputs are open drain. And we haven't discussed that yet, but open drain outputs are literally just one MOSFET. So you're going to have the N-channel FET going to the output. And I know I've been drawing it this way for quite a while because I really only need to consider one MOSFET at a time. But in a typical output, you're actually going to have 2 MOSFETs, the PFET and the NFET. But in an open drain device, there is no PFET at all. The NFET is the only thing driving the output, and that means the output only has 2 modes. It can either be sinking to ground, or it can be high impedance with this turned off. The way open drain outputs are typically used is they're going to be externally connected to a resistor that connects to the supply, called a pull-up resistor. And that means that whenever the output is in high impedance, this resistor will provide the charging current to make the output go into the high state. If you put 2 of these in parallel, or really any number of these that you want in parallel, then what's going to happen is whenever they both pull low, they're just going to be making the line 0 volts. They'll be in parallel. If only one is low, then the line will still be low. It just won't have as low of a resistance pulling it to ground. And the output will act a lot like an AND gate. If both of these are in the high state, that means both outputs are in the high impedance state, or in other words, no current is allowed to be flowing through that MOSFET. It's like they're disconnected. Then this output will become high due to the pull-up resistor. Any other time, if you make this low, for example, the output goes low and this will be forced low. So what happens whenever you excessively load an output? And what do I mean by excessive loading on an output? So if we take a standard CMOS output and connect it to a capacitor, we would usually call this a normal load, as long as it's within the datasheet specifications. Whenever you go to the timing and switching characteristics of a device, you're going to find that most of them are rated to 30 or 50 picofarads. Not very much capacitance. But with a 50 picofarad load, the device will continue to act normally. So whenever you switch your output suddenly from low to high, for example, this capacitor will be charged by the internal MOSFET. And as we stated earlier, it's going to start out with the MOSFET in saturation, driving as much current as it can. But because this capacitor is so small, it's going to very quickly charge up to a higher voltage, and the MOSFET will go out of saturation into the ohmic region, and then it will be charged up relatively quickly, usually within a few nanoseconds. And the question comes up, what happens if you increase this capacitor? Well, what we can do is take this capacitor and turn it into something completely absurd. Let's call it, say, a 1 farad capacitor. If you have this huge capacitor on the output, that means that pretty much regardless of what resistance you have internally, it's going to take a very long time to charge this capacitor. And the fact is that you're going to end up in saturation for far longer than this MOSFET can handle. Typically, you're only going to want your MOSFET to be in saturation region and driving a lot of current for a couple of nanoseconds max. In this case, we're looking at 10, 20, 30 seconds to be able to charge up that capacitor, and that's most likely going to result in our MOSFET overheating and melting. So there's definitely going to be some value between 50 picofarads and 1 farad that's going to be the maximum. Personally, I recommend to try to stick with what's in the datasheet. If your datasheet rates the device to 150 picofarads, then that's typically the most you'll ever want to load it. You can usually go to about 150% of what's in the datasheet as a rule of thumb. So if you have a 50 picofarad load specified in the datasheet, then you can go to about 75 picofarads without worrying too much about blowing up your MOSFET. If you have 150 picofarad, you can go to about 225 picofarads. There is an easy way around this issue though. So even if you have a 1 farad capacitor and you need to charge it up with a logic gate, technically you can do that. All you need to do is add a series resistor at the output of the device that prevents the current from exceeding the absolute max rating in the datasheet. In all cases, you should have a maximum rating, and usually that's going to be something between 20 and 50 milliamps. Say we want to limit our current to 50 milliamps. That's going to take a long time to charge a 1 farad capacitor, but it also will protect our device from being damaged. If you need to be able to do something like this that's kind of absurd, most likely you should be looking somewhere other than a logic gate for your driver, perhaps with some sort of discrete power MOSFET. Now the last and what I would consider the most interesting case is whenever you connect a logic gate to a transmission line. So I'm not really going to be able to go into a full explanation of transmission line theory in this video. However, I'm going to try to give you an understanding of what happens with a logic gate whenever you add a transmission line. One of the most important things to consider with a transmission line is its length. If you have a transmission line that's under 15 centimeters, for the most part, you won't see any transmission line effects. Once you start going past 15 centimeters is where you start to see those effects, and there are reasons for that, but again, beyond the scope of this video. So, whenever we turn on our driver over here on the left side, this is what I'm going to be calling the transmitter or the driver, then the receiver we want to pick up our logic signal. This transmitter is going to have an output impedance somewhere around 10, 20, 30 ohms, depending on the type of device. Let's just pick 25 ohms to have a round number. We're going to imagine that this is a very long transmission line, so long that we have time to talk about how things work in it. So in this case, we have a 25 ohm transmitter, a 50 ohm transmission line, and at the distant end, we have the input of a CMOS device. And that's typically going to be measured in mega ohms. So let's just go ahead and call that 100 mega ohms. So this is a huge resistance on the distant end. So the way this is going to work is our transmitter is going to attempt to switch the line with their 25 ohm resistance. And it will be successful. It's going to change the line from low to high or high to low. However, right next to this device, so we're assuming this is a very short trace going out to our 50 ohm transmission line, it's going to see what appears to it as a 50 ohm resistor to ground. So we could redraw this as an ideal buffer with a 25 ohm resistance and a 50 ohm to ground. It's 25 ohms here and 50 ohms here. You're going to get this voltage divider instantaneously whenever your transmitter starts sending its signal. And you're going to see that as a step in your function. So when your function tries to jump from low to high, instead of going up to high all the way, so let's say our high state is up here, it's only going to go 2/3 of the way in this case, because there's 75 ohms total, and 2/3 of the voltage is going to fall at this output node right here. Now that is going to travel down the transmission line. Now remember I said we have a long transmission line, we got enough time to talk about it. So that wave is going to travel down the transmission line, this step we've got, but it only goes to 2/3 of VCC. And that's eventually going to get all the way to the end and hit the end here, which is a 100 mega ohm resistance. And what that's going to do to us is it's going to produce a reflection. This wave is going to hit and it's going to reflect right back. But one of the things that happens when you see that reflection is the voltage over here, instead of being a step like it was over here, it's going to be a step that goes much higher than VCC. And the total voltage here is going to be 2 times the wave we sent down the wire. That's because it hits here and it reflects. They add on to each other. When that signal makes it all the way back, then we'll see the other half of that waveform show up, and we will see something along these lines where it will bounce back and forth, and eventually it'll settle out. Now, this is an incredibly ugly reflection that I've shown here, but I wanted to show it as very exaggerated to give you the understanding of what's going to happen if you have mismatches here. Now, ideally, in an RF system, which is not a CMOS system, to be clear, but in an RF system, you want to match the input and the output to the same impedance as your transmission line. So let's go ahead and match everybody up. I'm going to add a resistor right here. That's 25 ohms. So ignoring what we had down here, we're adding 25 ohms. So we've got the 25 ohms internal, and we've got another 25 ohms external. And that 25 ohms is now, from when you're looking back from the transmission line this way, you see 50 ohms total. Whenever we look the other way, we see our transmission line, that's 50 ohms. And at the distant end, we can add a resistor that goes to ground, and that is a 50 ohm resistor. So now we've terminated at 50 ohms also. Now what's going to happen whenever we transmit this? Now we've still got the same basic concept going on over here. You can draw your ideal buffer with 50 ohm resistor. And then we have our transmission line that also acts like a 50 ohm resistor. Whenever we have our 50 ohms here and 50 ohms there, exactly half of our signal is going to show up right here. So we will go ahead and look at VCC up here. We have our signal coming in and jumping up to half and then staying at half. At the distant end, whenever that wave travels all the way down our wire and it gets to the end, it still sees a 50 ohm resistor. There's no large impedance here. Nothing changes for it. It saw 50 ohms all the way down that wire, and at the very end it still sees it. So our signal at the end is still half VCC. And there's no reflection to come back. That's because everything was perfectly matched. And in an RF system, this is exactly what you want. But in logic, this is not what you want. You actually want your signal to get to VCC. We don't want to have half VCC. You can go back and watch my inputs video if you want to know why having half VCC on a CMOS input is a bad idea. But we definitely don't want that. So what can we do? Well, the easiest solution, and really what turns out to be the best solution in most cases, is to have exactly this circuit. We're going to have our resistance at this end that's going to match us to the transmission line. So our transmission line looking back sees 50 ohms. But whenever our transmission line is looking forward, it sees high impedance. So what's going to happen in this case? Well, same thing we saw before. We're going to be sending out a signal, and whenever we transition, it's going to jump up to half of VCC. And remember, it's going to take a while for our signal to travel down. Whenever it hits the other end, we've got exactly half VCC here because of what we discussed earlier with 50 ohm source and 50 ohm load from our transmission line. But whenever this signal gets to the distant end, it no longer sees 50 ohms, it suddenly sees high impedance. Whenever it sees that high impedance, it reflects. And what you're going to end up seeing is that that half waveform jumps up to a full waveform. So you end up going from 0 all the way to VCC, and it has a nice smooth transition. There's no stair steps or anything. You don't see much ringing. It's pretty much a perfect signal because it's only got this one reflection going on. You may get a little bit of ringing here due to inductance and other factors. But this is going to bounce back to the other end, and whenever it goes all the way back to the other end, we'll see the other half of our signal show up when that signal reaches the other end, but it doesn't bounce back a second time, and that's because when you're looking this direction, you have 50 ohms into 50 ohms. That waveform travels down, it sees 50 ohms the whole way down, and then when it gets to the end, it sees 50 ohms, and everything remains matched, no reflections. And this is what's called a source termination for a transmission line. Your transmitter is the only place where you terminate, and you're going to get your full waveform at the distant end. And this is the ideal way to terminate a logic device whenever you're trying to communicate over relatively long transmission lines, that is 15 centimeters or longer. Let's go look at a datasheet and see how you can interpret the datasheet specs to get the details you need to do these types of calculations and to make sure that you're not using a CMOS output incorrectly. In this case, I grabbed an LVC family buffer, and this device is going to have the details that we need to calculate the output capabilities. The first table you come to is the absolute maximum ratings table. This table is going to tell you what not to do to the device to avoid damaging it. So the most important thing for us when we're talking about outputs, we're talking about continuous output current. So whenever we apply a current to our output, 50 milliamps is the most we can apply before breaking the device. And this is going back to what I said about having large capacitances on the output. If you were to put 500 picofarads or 1 nanofarad on the output of a logic device directly, it's going to be driving more than 50 milliamps for a significant period of time, and that can cause this device to be damaged. Now I hear you saying that right there in the table it says the output will clamp to 50 milliamps, so there's nothing to worry about. But that's not what it means by output clamp current though. This is specifically talking about the clamp diode placed at the output. Note that it says Vout less than 0 volts. So if you were to drive the output below 0 volts, you could turn on that diode, and this is the maximum current that you are allowed to drive through the diode without damaging it. It's completely unrelated to the output drivers we've been talking about. Something else to consider here is that the continuous current through VCC or ground can't exceed 100 milliamps. Now, because this is a single buffer, it's not that important. But if we had a double or a triple buffer, then we'd have to start worrying about this, because if you have 3 outputs and all 3 of them are trying to drive the maximum of 50 milliamps, then you're going to exceed this 100 milliamp value and you can damage your device. Generally speaking, you don't want to come close to these numbers. There's no reason to with logic for the most part. Something that's fairly confusing to a lot of people is that there are recommended operating conditions for the IOH and IOL values. These are the high-level output current and low-level output current. For example, at VCC equals 3 volts, there's 2 different numbers. It says you can either have a max of 16 milliamps or a max of 24 milliamps. And that doesn't really make a lot of sense. But remember, these are recommended values, and there's a reason these are the recommended values. Let's go down to the electrical characteristics table and see why those are recommended. Here you can see that the output high state voltage at 3 volts is going to have 2 different values. It has one value for a 16 milliamp output, and it has a different value for a 24 milliamp output. Now what's neat about these numbers is these are going to directly tell you the resistance of the output of the device. Let me grab my calculator here really quick. Assuming that we're operating our device at 3 volts, which is what the supply says here, 3 volts, and the output voltage is 2.4 volts, then that means my PFET has 3 minus 2.4 volts across it, so 0.6 volts. I can take that voltage and divide the amount of current, which is 0.016 or 16 milliamps, and that tells me that my output has a resistance of 37.5 ohms in this condition. The very important thing to remember here is that these numbers are maximums. So whenever we look at this, this says minimum across minus 40 to 85C and minimum from minus 40 to plus 125C. In other words, you should never see this number when you're using your device. This is the worst case, typically with some added headroom to it. So that 37.5 ohms is also the worst case. And in this case, worst case means higher resistance. So technically, you're going to see a lower resistance than that 37.5 that we just calculated. And in fact, the typical value, if you run across the majority of logic datasheets, you're going to find that it's half. 18 or 19 ohms is much more likely to see than 37 or 38 ohms. For the output low state voltage and output low state resistance, it's much easier to calculate because you don't even need to know the supply value, because remember, the supply is what's controlling the MOSFET. The output voltage is what's directly across VDS. So really all you have to do is get your calculator out, take the voltage at the output. So let's look at that 4.5 volt value. So 0.55, divide by the current, 0.032, and we see that the maximum resistance under these conditions is 17.2 ohms. Or in other words, we're looking at around 8 or 9 actual ohms for typical operation. I hope this video has helped you to better understand the output structure and output capabilities of a typical CMOS logic device. If you have any questions, feel free to post them in the comments below, and thanks for watching.